So this video is about one-dimensional wave interference. So basically what happens when two or more waves interact with each other in a medium and the properties that you should notice when this happens. So interference is the term we have anytime you have multiple waves trying to travel through the exact same location, the exact same moment in time. Kind of like how if you have I don't know, I tend to think of hockey when it comes to this. My first thought is the best way to score a goal is just to skate in front of the goalie and then take him out. Just knock him over. But in my head, that's two people trying to occupy the exact same spot at the exact same time. It's not really possible. And so if you're doing that in the game of hockey, the referee will blow its whistle and you'll get a penalty because you are interfering with the goalie. You're trying to be at the exact same spot at the exact same time as the goalie. So that's how I think of it sometimes. You guys can just ignore that if you want. Interference is when you have two waves or more trying to propagate through the exact same space at the exact same time. So I've got a bunch of animations, if you will, for this one as well, about what it looks like when you have two waves interacting with each other. And typically when that happens, you're going to have something known as superposition. So interference is when two waves interact or more interact with each other. Superposition is what happens to their amplitudes. So the superposition is the actual adding of their amplitudes together. Crests would add to crests and become larger. Troughs would add to troughs and also become larger troughs. But when a crest interacts with a trough, you would actually subtract you'd still add, but crest would be a positive value, trough would be a negative value as far as amplitudes are concerned, and they would just make smaller amplitudes in the end. So back to Surendranath's website from a previous video. This is just going to show some quick little animations of what should happen. So here you got two crests propagating towards each other. The red one's going to the right, the blue one's going to the left. And essentially what would happen is the two crests would just travel through each other. The red is still going to the right, the blue is still going to the left, and they would just add up together. So you can see that they are 2 lines high, so we'll call it 2 units of amplitude. When they interact with each other, I'll stop it right there. Their 2 amplitudes add up, and now you have an amplitude of 4. All right, the wavelength shouldn't change, so this was specifically made so they have the exact same wavelength. Let's just step back. So they have the exact same size wavelength, so the actual wavelength shouldn't change, only the amplitude changes. So when you add the amplitudes together, we call that superposition, but this is just wave interference. This is the phenomenon wave interference. Physical adding is the superposition. So and specifically, we would call this one constructive interference because you have 2 crests interact with each other and they make a larger crest. If you had 2 troughs interact with each other, they would make a larger trough. So this time I've got unequal amplitude. So this has an amplitude of 2 units. This is an amplitude of 1 unit. When they interact, you get a total of 3. So you're still going to add them together. If I make them out of phase, so that means in this case they are 90 degrees out of phase, where one is a crest, the other is a trough, you end up with that kind of interaction. They call that destructive interference. Sorry, 180 degrees out of phase. This is known as destructive interference. So anytime you have a crest overlapping a trough, their amplitudes add together. Oh, they're not equal amplitude. Their amplitudes add together. You have a 2 amplitude red and a -1 amplitude blue. So this is our crest adding to our trough. +2 added to a -1 gives you a final amplitude of 1. So in this destructive interference, you have a smaller crest because the crest was bigger to begin with. If I make their amplitudes equal to start with, when they interact and have destructive interference, if I pause it right at the exact moment of time when the 2 waves are completely over top of each other. Now again, these are the exact same length of wave, right? This wavelength here for the crest is the exact same length as the wavelength of the trough. At this moment in time, when they are completely overlapping each other, they have canceled each other out. So this is complete destructive interference. And to watch that in real time is kind of neat to see. So I've got a real-time video for that that I'll show in a moment. So that's just your wave addition is typically what it's called in physics. So otherwise known as superposition, typically in class, because obviously you can't have animations on your paper. This is usually how I represent it in class. You would have your constructive interference, you'd have a small crest added to a much larger crest. They should have the exact same speed because they're traveling in the exact same material. In this scenario here, velocity 1's just going to the right, velocity 2 is going to the left, but numerically they'd have the same speed. Let's call it 2 meters per second, call that one 2 meters per second as well. The moment that they interact, and I did just draw this by hand, so I can't really guarantee I have the exact same wavelength there and there, but go with me on this. So if they have the exact same wavelength, their wavelength shouldn't change. The only thing that should change is their amplitudes will add together, and this is the superposition where your two amplitudes add together. Amplitude of 4 added to an amplitude of 6 is an amplitude of 10. If this is a trough added to a trough, I would just have a -4 and a -6, but you get the exact same idea. And the waves will just go through each other. They will not affect each other whatsoever. Right? As you saw in those animations, the red wave going to the right wouldn't be slowed down with the blue wave going to the left. They would just go through each other, they'd add up for a brief moment in time, and then just keep continuing propagating through. They do not bounce off each other. So destructive interference, similar idea, you're still gonna have superposition, but your waveform, your amplitude, pardon me, your amplitude should be smaller in the end. So I started off with a large crest, so 10 amplitude crest. I have a 4 amplitude trough, so -4 would imply it's a trough. And so when you have a large crest compared to a small trough, at the moment of interference, so when you superimpose the two waves together, you'll just have to subtract the two. So 10 added to a -4, or just think of it as 10 - 4, you'll only have a 6 millimeter amplitude. So the trough takes away from the crest. If I had a larger trough compared to my crest, I would just have a smaller trough in the end. So this would be your destructive interference. I have a little video from class a couple of years ago. Typically you'd be playing around with slinkies in the classroom to kind of see this for yourself firsthand. So there is an example. They put it in slow-mo. I'll let it play again. So pause. I have a crest coming from the left. I have a trough coming from the right. They're about the same size and amplitude. They're about the same wavelength. They were just making these by hand. And so at the moment of interference, so they're now gonna go superimpose on top of each other, right? I just missed the pause. It canceled out just ever so. It wasn't a perfect, so that's about as close as I can get to it completely canceling out. So it almost flatlines altogether, which tells you that their wavelengths are just slightly different in size as well as their amplitudes, but they were pretty close. If they were perfect size amplitude, say again 2 units crest, 2 units as a trough, it would have been a flat line completely. So that's pretty close for just using your hands. And of course it reflects, they're holding at both ends, so crest turns to trough, trough turns to crest, and they just go through each other. They do not bounce off each other. The crest, still a crest after the interference. So that would be your destructive interference. So the next question is, well, what happens if you have the exact same wave? So I have a little animation here. It's my cat. Go away. I have one wavelength propagating to the right. I have the exact same wavelength propagating to the left. Right? They are the exact same waves. They're just traveling at different rates. One's going right, one's going left. They have the same frequency. They have the same speed. They have the same amplitudes. They're just traveling in different directions. So when these two waves superimpose, they're going to get a special kind of interference known as a standing wave. So standing waves are very special because they are showing that you have superposition, but there's this little spot right here that is in quite a few places. Right? When you get a standing waveform, this pattern is a little bit known as resonance. And when you have resonance, you're going to have a series of nodes and antinodes. So nodes are points in the waveform, in the interference, where you constantly have a crest canceling off a trough. Right? You'll notice that it's a bit hard to notice here, but at all points, for every positive going up as a crest, the exact same numerical values at trough going down will always cancel this spot out, as well as that, as well as that, as well as that, and we call those nodes. There's absolutely zero movement in the medium. Right? This string would remain perfectly still at that point, at that node. Whereas this point right here, known as the antinode, often known as a loop, because if you can make this animation go faster and faster, this, if I just casually, oh, I can't draw to save my life. If this was in real live motion, if you're in my classroom and I had a string hooked up to my generator, I'll show a quick little animation of that too. It would, your eye would not be able to see it go up and then down. It'd be happening too quick, and it would just literally look like this is forming a loop. And so sometimes these antinodes are known as loops. So this is where it goes from constructive to destructive to constructive to destructive. So it's constantly going back and forth between when two crests line up, then it goes up. And when two troughs line up, it goes down. And anytime a crest lines up with a trough, it cancels out completely on this line of equilibrium. So that's where all the movement is occurring, at the antinodes. So this is just a different version. So you've got the exact same wave traveling, transverse wave traveling to the right with traveling to the left. So you've seen that animation. This is what it looks like if you have a longitudinal wave or a compression wave. Right? You can see those compressions of these particles as it propagates to the right, and the exact same wavelength propagating to the left. And when you have a standing waveform using compression waves or longitudinal waves, it just looks like all the particles are constantly going back and forth in a spot. And that is typically why we call it a standing wave pattern, because it doesn't look like the wave energy is traveling in any one direction. It's just going back and forth in the spot. Unlike over here, it looks like everything, the energy is going to the right. This one has the energy going to the left. Over here, it's just going up and down. It's just bobbing in place. That is known as a standing waveform. So standing waveform pattern, those are the notes. The key thing to remember is your node or nodal points, and your antinodes. Sometimes in still form, you would label a node as an N. Other times you label your antinodes as AN, as an example. And that would be just your different types of interference. And I think I will stop the animation, the video here.